I draw a P sub. What is this one? This area? No, the big one. N-well, right? N-well, which means it's going to open up the fox, right? You don't have to draw the fox if you don't want to. It's okay. So here's going to be the N-well. The line is drawn here. And that's a gate, right? So the gate is on the top of P plus. And here's a P select and P active. So which one defines the area of the P plus? P active. The inner one, the outer one. Yeah. So here's going to be the P plus. Here's going to be the N-well. What else do I have? Poly, right? Is this going to be covered by another oxide or not? Here. There's the oxide layer because here's a gate. In between the gate and whatever here, there's a oxide layer. You don't have to. And the poly is in the middle. It's not directly attached to the bottom. That's so there will be something to isolate it. But is there a layer here? When it deposits a oxide layer on the top, there might be something here. I'm not sure actually right now. It looks odd. I think I upload a picture on the website. Let's take a look at it. Because the fox is not directly just a rectangular shape. Oops. Electronics.com. Yeah. C5, I think I uploaded. Oh, here. Got it. So this is the ICM cross-sectional view of the. I think the CMOS. I don't know actually. I don't know what's the material here. But what I want to show you is what's happening actually over here. Right. So did you see the fox? That's why sometimes it's confusing. If I directly draw the fox like a rectangle, it's not like that. Where is fox? So what is diffusion? Remember? So you put the chip in the vacuum and dump all the molecules in there, like N-type, P-type. So it's hard concentration in the environment, so to diffuse through the wafer, right? So that's why it's called diffusion. So these are either N plus or P plus, right? This area. And what is this? Yeah, via. So what is this? Metal one. So what is this? Not yet.
Is that the oxide there?
It's silicon dioxide.
Yeah.
For each layer, you have a silicon dioxide for each layer, right? Okay. So see this layer here, that's a fox. That's fox. See, fox. Right. So if you don't have a via on the top of the diffusion, there should be a fox there. See? See the fox? Fox? You don't have to, I think. I mean, for the cross-sectional view in the future, you don't even need to show the fox. It's not a functioning layer. It's just something in the middle. And what is this? Poly. And there's a very thin oxide layer here as well. It's called gate oxide. looks like there's nothing, right, directly attached to the P stop. It shouldn't. It shouldn't, right? Otherwise, it's going to be conductive. It's not. It's a semiconductor. It's a dielectric material in the middle, and you apply. It's very interesting, right? Why there's nothing connected to the gate? The gate is not shorted to anything. Does that make sense? So cannot turn on or off the transistor. Yeah. Then why? Yeah, I think so. You know what I mean? When the place they cut that poly doesn't have that via. If you move back a little bit more, then probably you'll see the via and cut it, you'll see the cross-sectional view. But that's what I'm thinking. Right? There must be something connected to the gate. Otherwise, why do you have a gate? Yeah. And I don't know what what is the name of etching artifact. Yeah. I don't know. Oh, for vias?
Oh, I see.
So it's able to hold more metal in there? Not sure. Oh yeah, this is metal too, right? Yeah, it doesn't have that shape. So probably this one has a via somewhere else. Connect to metal 2. Otherwise, you have metal 1 here not shorted to anything. It's not making sense too, right? So it's probably at some point it's shorted to metal 2. Okay, so now you know what the fox looks like. Okay, so don't get confused in the future. Now let's finish this cross-sectional view. So there will be something on the top, right? If you don't draw it, I won't take points off. Actually, it's not a functional layer. Anything else? Here's a poly, right? Poly is this long. So we got a poly here. Remember the poly is in the middle. Draw the poly. Do you have a via connect to the P plus? The vias are here, right? But if I draw a line here, there's no connection. The dielectric material is it isolates the gate from the P plus. And then what is this material? Metal 1. So need another layer. And just draw metal 1. It's this long. So this is metal 1. And here's a little via here. Right, and that's it. Some of you just drew a lot of vias here. Doesn't make sense, right? The poly shouldn't have any, there's no via by looking at the layout. And also the gate shouldn't have any direct connection to the P plus. Right. Make sense? Yeah. All right. No question on this one, right? Easy. AOI logic, very sexy technology. And or inverter. So it has PMOS is on the top and NMOS is the bottom, and the logic is has a bar on the top. Why? Because when you turn on the PMOSes, the input is 0. But however, the PMOS is short the output to 1. So that's why I have a 0 input 0 as the input, but the output is being put out to VDD, so it's a 1 there. Right, so I have to invert it in order to get the right logic. How do we form AOI logic for the XOR gate? So this is XOR, right? Remember the A, so this is a NAND gate, right? So NAND gate, we have 2 PMOSes in parallel on the top and 2 NMOSes in series at the bottom. And here's A, B, NOT. For NOR gate, the output is not AB, A or B. It's A or B NOT. Okay, so I have to invert it in order to get the A or B. Otherwise, it's a NOR gate. So for this one, if you want to use this kind of logic circuit, yes, definitely you can use the individual logic gates to form this logic. But remember how many gates we had last time? How many I drew there? For XOR gate. So remember on Monday, this is what I did, right? It's something you are expecting for XOR logic. This is XOR logic. These are all the gates. We just look at the logic equation. Okay, this is what you are going to do if you don't optimize it. Okay, and now let's compare. If we want to use the AOI logic to form the XOR gate instead of using the individual logic gates, remember the output here is always has a bar on the top. So if you directly form a logic from here, then you have to add an inverter after it in order to invert it back. So what you can do is A, so this equals A not B or A B not. So it's not changing anything. And then use the De Morgan's law. Remember what is the De Morgan's law? You can split the bar and change the sign, remember? So it's like A and B not equals split the bar, change the sign, A not or B not. A or B, split the bar, change the sign, which is A not and B not. Okay, just remember this one. It's from logic 1, but not logic 1, just C241. So here's the conclusion. We're not trying to derive it, but just keep in mind. Okay. Let's deal with the bottom part first. Split the bar, change the sign. So keep the top bar here, but split the bar, change the sign. You are getting A not B not and A B not. Is that correct? You split the bar here, right? Split the bar, change the sign. Yeah. Right. And then this equals split the bar, change the sign here for each of them. You are getting A not or B not and A not or B not. And this equals A or B not and A not or B. And this equals A and A not or A and B or A not B not or B not. And these are zeros. Something or 0 is still something, it's still that same, right? And this equals A B or A not B not. Why do we do that? So there was a conclusion. I don't know if you ever still remember it. A XOR B equals A X NOR B not. So what is A XOR B? Is A not B or B A B not? What is A XOR B? This guy is A B or A not B not? Boring. Yeah, conclusions from logic 1. Just keep in mind for XOR logic, you have the bar on A and the other one on the bar on B. But for XNOR, right, XOR, for XNOR logic, it is just A, B, no bar at all, and then bars on both of them. That's XNOR logic, that's by the definition. And here's the conclusion of it. And here's how you prove it. See, this is XNOR. Put a bar on the top equals the XOR logic. There's something you need to know. Our fundamental logic knowledge here. But are we trying to prove that you invert the XNOR logic, you are getting the XOR logic? What are we trying to do? Yep. And why do we get here? Why we spend the time on this? Remember, whenever you are trying to convert, because logic equations can be anything. Can be A not B. It's just a logic equation, depends on the application, depends on the customer, right? You can have A, B, C, or B, C, D, E, whatever, right? But if you want to convert that logic equation into a real circuit, not just using individual gates, because it takes space and so many transistors. However, you want to use AOI logic to form all the circuits, to implement that logic. You need to put a bar on the top eventually in order to start designing that circuit. Let's do it instead of just explaining everything. So now we got here. How do we convert this one into a transistor circuit? This can be really fun. You'll enjoy doing that, to be honest. Now let's take a look at it. When you have a AND logic underneath the bar, you need a parallel PMOS on the top and series NMOS at the bottom. You know what I mean? Keep in mind, whenever you have AND logic underneath the bar, you do this. If you have OR logic, like a NOR gate, you put a two PMOSs in series and two NMOSs in parallel. And that's everything you need to know to work on all the other logic equations. I'll start with this one. Okay. AB is AND logic. So what do we need for these two inputs? Oh, yes, in parallel, right? Let's do the PMOS first. Start from the top. And this, if you treat this one as one entity, this one another entity, it's a NOR gate, right? It's OR logic. So need these two to be where? In parallel with these two, or just underneath in series? Remember the NOR gate? Always think about the NOR gate in series. So this is A, this is B, this is A naught, this is B naught. It's just the input. You see this, how to get A naught? You just have to invert it somewhere else, right? We're not doing it here. It's just a signal. And now the PMOS is done. PMOS part is done. Now look at NMOS.
Why are we shorting the left and right side?
Because they're in series. It's like in series, right? There's no difference. Same. It's just one wire.
Right.
You melt the metal. You can put them together. What about NMOS? Still look at this equation here. AB is the unlogic, so they need to be in series, right? For the NMOS. A naught, B naught should be in series. And I put these two in parallel because this is a NOR gate logic. Remember the NOR gate for the NMOS, they're in parallel. The two entities are in parallel. So these are the two entities in parallel, right? That's ground. So now I want to ask you guys if this one is A, X, or B or not, or do you need to invert it one more time? Take a look at it. That's it. Yeah, because they have an inverter on top, which is perfect. And we are forming this logic by looking at these two, right? And there's a bar on the top. So we don't need to invert it. If it doesn't have a bar on top, we have to invert it. Like these guys. Right? When you're just dealing with A and B, A or B, you form this circuit. You don't need to look at bar. But whenever you are done, you should know that it has a bar on top. Because you have to turn on the PMOS, use a 0. Yeah, you don't have to always think about that why, right? After you know this is correct, just directly use this technique to design all the circuits in the future. One more question. If we do not have, if you don't want to do it, do we have to have the second method to form this logic instead of using the bar on the top of XNOR? Can we directly do this using a different way? We don't have a, sometimes you don't want to add a bar on the top and you don't want to derive all the equations to here. When you want to add a bar on the top, you have to put 2 bars and use the De Morgan's law until here, right? Can we directly form the circuit by just looking at this one? Can we? Now let's look at it. So it's A naught B, right? It's A naught B. It's unlogic. So do you need a PMOS in parallel and series? Parallel. A naught B. What about AB naught? That's the OR logic. So need these two in parallel, but also for the entire thing here in series with the top one. This is A, B naught. Now A naught B it's unlogic, so they need to be in series. A naught B. This is A, B naught. Same circuit, but what's the difference in between these two circuits? Inputs, right? It's the same circuit, there's nothing different. Is that correct? Right? It's the same circuit. So we follow the same rules. Whenever we see unlogic, we just draw 2 parallel PMOSes and 2 series NMOSes, right? So the circuit looks like it's exactly the same. However, the difference is, see the signal, here's A, here's A bar, here's B, here's B. A bar A, B bar B bar, right? So the signal is different. So do they output the same logic or not? No. So what's the logic here? What's the output here? So we were looking at this logic equation to form this circuit, right? So does this one have a bar on the top? No. So when we look at this equation to form a circuit, this is actually whatever. Yeah. So this is what this circuit does. However, we are trying to get this equation, right? Get this logic. So what we have to do is add an inverter here to make X work. So this is actually X norm. This becomes XOR. Which one do you prefer? XOR, XOR, right? Same XOR. Which one do you prefer? This one, right? Either. Or less number of transistors being used. Now we know the schematic, and we need to move forward with layout. So by looking at this schematic, how do we design the layout? It's pretty fun. I like it a lot. How do we do the layout? Two rails, right?
Yeah.
PMOS, two PMOSes in parallel. Can we direct? So four PMOSes, right? Four PMOSes. Let's see if we can do it. I'm not really sure. 1, 2, 3, 4, 5. So 1, 2, 3, 4. We have 4 gates, which means we have 4 transistors. How many gates do you have? How many transistors do you have? Okay. 4 gates, 4 transistors, 4 transistors, 4 gates. Okay, so we have 4 transistors here. So these are all connected in series or not? You don't know yet. You don't know yet. Depends on the connection. I haven't done that yet. You know what I mean? I just draw them that way. But I can configure the circuit in order to make it in parallel in series. You can see the 4 transistors are not totally in parallel or in series, right?
Yeah.
Have to design it. So 2 transistors in parallel and then other 2 in parallel and then eventually in series for all of them. How to do that? So remember 2 parallel transistor, what you can do is this, right? Like currents flow from here and merge to one. So these 2 transistors are in parallel. What's happening is the currents flow that way and cross that gate, so got 2 transistors in parallel and merge to this point. What's next? Does it work? Is this going to work for the bottom 2? And why not? So from the ground, from the VDD, right? VDD split into 2 branches, right? And then merge here, okay? And merged here. Yeah, this is better actually, right? Split into 2 branches and flow down here and merged here and then flow into here. And whenever, so the point that merges the 2 currents has to be shorted to 2 transistors or to the drain that can be split into 2 transistors. But can this point be split into 2 transistors? Can we do that? So this is where, so this point is this point, right? It's not going to work. Why? Because the VDD is shorted to, these 2 transistors doesn't have any VDD connection. As you can see here, these 2 transistors has one of the node being shorted to VDD. So when I firstly, at the very beginning, when I was designing the parallel PMOS, I shouldn't do it that way. I have to change the strategy here. So this doesn't work. So what's the alternative way to do it? So we want to introduce 2 wires here, right? Can I introduce just 1 wire? And then split into 2 branches? And merge? So this point becomes this point right now, right? Make sense? Then what's next? This may work because this is a point that merges, and here is the drain of the, one of the two PMOSes, and which makes sense here right now. It's not shorted to VDD at least. This one is somewhere down at the circuit. This one? Yeah. So do you want to do this or this? Why? Huh? Yeah, because you have to introduce a wire here in the future, right? It's going to short with this metal one. You know what I mean? If you short to here and then they merge here, I have to introduce a wire here. This is going to short to this metal one. So if I do it like that and then do this, this will do the job here. Any questions? Let's go through this again. That helps. Okay.
This part's fine. This part's fine.
Yeah. Mm-hmm. VDD comes down, split into two branches. VDD comes down, split into two branches and merge. Split into two branches and merge. Okay. It doesn't matter. It's here, 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 or here, here. It's just one voltage node. It's the metal piece. Okay. So this point is going to be this point. And you need to split this point into two branches and flow through two PMOS transistors. How to split it? Here's how you split it into two. One branch, the second branch. And merge to here, and merge to here. Okay? What about PMOS, NMOS? The same structure or not? No. You don't have a wire here, so they're different. How many transistors? 4, right? So you need 5 nodes. 1, 2, 3, 4. Is this easier or more difficult? Just two branches, and each of the two transistors are in series. What could you do? Go to the sides or go to the middle? If you go to the middle, split. Two transistors in series to the ground. Right? Split, split. And you can ignore that node here because there's no connection. There's no metal one need to be introduced from that node. What is this gate? Yeah, the actual gate. I'll do this one. Which one do you prefer? Yeah, a lot better, right? Yeah. So that's why you want to use AI logic, so you can manually optimize the circuit. Only when you are manually optimizing it. But when people design the Apple like A12, A14, I don't know the name, it's just evolving so fast. And Snapdragon CPUs, do they optimize these? Yeah, but do they optimize the gates like that?
Yeah.
No.
They don't optimize the gates?
Optimize the gate, let me see. Individual gates probably because they are in the library. So the whoever sells the standard library cells to the company, so the gates may already optimized. If you put two gates together, you can actually manually optimize two gates together sometimes. You start working on that in the Photon labs, but they won't optimize the two gates. They just grab a gates, put in there, and automatically routed everything. So there's no way to optimize it. Just billions of transistors, no way to optimize it. Just let it take the space.
You can fit more. Yeah, you can fit more.
So I think the synthesis tool, the EDA tool, is able to optimize something, but won't be like this. So the manual layout is still the best in terms of space and looking, I guess, as well. Have to look at it under the microscope. Have to be able to afford it first. We don't care about if it's pretty or not. We just care about if it's able to stream YouTube videos, right?
That's what we thought about deep learning. I don't know.
Let's look at a different example.
Trying to tear it off. But
I actually have a different version of it. See, is this correct? Let me double check. Yeah, there's another way to do it. Show you.
what was wrong with that last method?
This is good.
Oh, were you doing the?
There's another one. If I have what I put on my notes is a different design. Let me see if this makes sense. So if I connect a wire in the middle and I merge it here and I do it here, is that the same logic? Same circuit? Could it do the same job?
Splits into two and then it merges and then it's two again.
Yeah, in here, split, and merge, right?
Yeah.
It merges here, so these are the same nodes, right? The same node, and same node is being split into two branches, and then merge. Same thing. You don't have to change anything for the animals. It's very straightforward. Use the same structure here.
How do we know what structures an XOR and
You don't. You gotta look at the signals.
What you mean?
Well,
We
they're the same structure.
oh,
it just
XOR,
depends on the input.
no.
oh, you mean, yes, different inputs. That's right. Same circuit, right? Same circuit, but different signals. Yep.
Is there an easy way of remembering which one's which, or does there?
What do you mean which one is which? The circuit is the same.
Well, right, but like, is there a way of remembering, like, oh, the X node is A dot A?
You are not remembering that. You've designed it every time. Even now, if you let me just look at the circuit, it takes me 10-15 seconds to find out the logic equation. You don't have to. Whenever you have a logic equation, you start from there and design the circuit from the logic equation. You don't have to memorize this, right? Do you? You don't. Let's look at more examples.
Which one's two diagrams?
What you think? We can think about it. Which one's better? What you think? I prefer this one.
Less connections.
Because if you do, this one is okay as well because it eventually merges here, right? There's no shorting circuit. It's not shorting to any of the traces here. There's no difference.
Okay.
It's more symmetric. If that helps a little bit, sometimes the signal transmits to the PMOS at the same time, so you can synchronize the signal. But I think the difference is tiny. Unless you are running this circuit at like 4 gigahertz or something, there might be a little difference because this split into two, right? And then I think you need a trace to connect to this one and then get a parallel PMOS, but this one directly enters the PMOS here. So this takes longer time. If you have a little bit timing difference, there might be a little glitch in the signal.
So if we have two like equivalent circuits, we should favor the one that's
More symmetric, I think so, yeah. But based on the speed we are running for the circuits, they are usually like kilohertz. You won't be able to see any difference. Let's look at an arbitrary logic instead of just a standard XOR or XNOR. What if something like this, y equals A not or BC? What about that one? Implemented using AOI logic. If you don't draw a bar on the top, you follow whatever the AOI logic, you can draw a schematic, but you have to invert it. So let's do it. A or BC. So here's a NOR gate. That's a NAND gate. So this must be in series with these two. And these two must be in parallel. Make sense? That's the PMOS part of it. What about the NMOS part? For the OR logic here, always think about the NOR gate. The two NMOSes are in parallel. And for the NAND gate, these are in series, so you got B and C and A not. Anything else? Anything else? Mm-hmm. So this is A not or BC. So if we simplify it, spend a little bit more time on it, this becomes split bar chain design, keep the top bar, you got A not not and B C not. And this becomes A and B not or C not. And this becomes A B not or A C not. It's the perfect structure we want to see at the bar on the top, and that's AND OR logic at the bottom. So A, B not, they are in parallel series with PMOS. Parallel, right? Because this is NAND gate, always think of the NAND gate. Remember, NAND gate has a parallel PMOS on top. And this is NAND gate as well. And this is NOR gate. So NOR gate has the two structures, two entities in series. And then and this is A or BC, right? Here, this one. You got 5 on, oh, 4, 4. It's the same number of transistors, but let's see if we can merge the 4 PMOSes in one line. So you want to try the best to make everything in one line. Sometimes you can save a lot of space by doing that. Otherwise, you have to have another transistor just beside it, right? In the same line, but they are separate, which will take more space. So if you can make everything one line, we just did it, like this structure, just different signal, but same circuit. And we can do it, we can use this, we can make this one into this, right? Into this. But can we convert this one into something in one line? Let's try the PMOS really quick. 4 transistors, 1, 2, 3, 4, 5. 1, 2, 3, 4. Can we convert into one line? These two are both VDDs. So if you want to convert into one line, you have to introduce the VDD here, because this becomes the inverter's PMOS, and this becomes these PMOSes. And could you do this structure here? So 1 and 2, 1 and with 2 in parallel. Could you do that?
Yeah.
How?
Just go from put the first and third ones together.
Does that make sense? So if I put this guy on the top and these two at the bottom, is there any difference if I put this one at the bottom and this two on the top? No difference, right? The 2 parallel PMOS on the top and this one at the bottom, they are still in series, no difference. So this is what I'm doing here. So this one is the inverter's PMOS, right? No problem. And this one is a NOT. Oh, I didn't invert, I didn't swap it. Anyway, sorry. So this is a NOT, and then here 2 in parallel, and this is B, this is C. And here's a wire here. So this guy just got lucky. You're still able to do it. But if you have more transistors, sometimes you just couldn't put everything in one line. All right? Nothing on Friday. See you guys on Monday. I forgot if I have it. Yeah. I didn't put anything here, so the quiz is on next Friday, which makes the break a little nicer.